In the last presentation, we alluded to a quantum wave function. We know that the quantum objects exhibit both a wave and a particle character. But what is it that causes it to turn from a wave into an object, or turn from an object into a wave? How can it have both of these characteristics at the same time? Well, the answer is that it can't, is that it has to, at any given point, it's exhibiting either a wave or particle character. And the wave function is the way that the wave represents itself that creates an abstract space of potential, which then is selected out of this space to then actualize into a single quantum object. So the wave function contains all the dynamic information about the system it describes. So it is basically a descriptive function. It is a descriptive representation of all of the potential states that the quantum object can take on. So the wave function itself is an expansive space of potential values represented by a graph that indicates the probability of a quantum object having a particular position or momentum. The wave function psi is the probability amplitude, and the wave function square gives the wave function's probability density function. So that means that when you take the area under the curve between two positions on the graph of the square of the wave function, you'll find the probability of finding the particle at that interval. So the Schrodinger equation is a differential equation used to predict the distribution of energy in a quantum. It is time independent, which means that it does not change with time. At any point, the operator is basically equal to its energy distribution. The equation is astonishingly simple. You can see it right here. H hat psi equals E psi. So psi is a Greek letter that represents the wave function. H hat is the Hamiltonian operator, and E is the energetic distribution of the wave function that the quantum operator brings about. So you don't need to know this, but if you're interested in the math, you can see it in the corner that the Hamiltonian operator H hat is the second derivative of Planck's constant squared divided by twice the mass of the quantum object. So that's H squared over 2m is, and then the double derivative of that. So that is basically what that is. If you're interested in the math, that you can learn that. You don't have to. When you plug all of the values in, you can calculate the probability of a particle's position at any range of values simply by finding the Hamiltonian operator, finding the wave function, and then taking the integral of that. So basically, you're finding the area under this. You can plug this into a graphing calculator. You can make a graph and then find the area in between 2 points, and you divide the total when you divide the total area by the when you divide the area between 2 points by the total area, that will give you the probability of a quantum object occurring on that interval, or at least the actualized state of it. So basically, this allows us to predict the probable positions at which quantum objects will end up. Again, we can't predict the exact position because there is no exact position. There's no determinacy at the quantum level. We have to think, what is it probably going to be? What is it likely going to be? But we can't know, like in classical mechanics, definitely where it is going to be, because the quantum world isn't predictable like that. We just have a function that represents where is it likely to be, and then it's actually the operator that decides. It's not us that decides, it's the operator. So the operator is working from this space of potential, and then it selects one potential and it says, okay, that's what we're going to actualize. That's going to become the energetic distribution of the system. So when you plug all the values in, again, you can calculate the probabilities of the particle's position at any range of values simply by using an integral and placing the Schrodinger equation within the integrand, as you might learn in an upper level high school math class covering calculus and statistics. The equation can be represented in the form operator times function equals the constant factor times the same function. So basically H is the operator on that function. So the operator as applied to the function equals the energetic distribution times the function. So that means if we divide both sides by the wave function, if we divide both sides by psi, then the Hamiltonian operator actually equals the distribution energetically of the particle, meaning that we can represent that which transforms the wave function as the space of potential that the probability distribution of the values that the operator can take on. So E is called the wave function's eigenvalue, German for intrinsic value. The wave function distribution assigns a probability amplitude to each possible configuration of the quantum wave function. So the operator on the quantum function that assigns these scalars to the energetic distribution is called the eigenfunction. So eigenfunction times wave function equals eigenvalue times wave function. So eigenfunction equals eigenvalue. There is some equality relation. There is something that is connecting the wave function, the quantum wave function, and its collapse state. So it's called a quantum wave function collapse when that space of potential, when that operator then transforms the wave function to become a definite value of position or momentum or whatever characteristic or attribute that we're talking about. So what the Schrodinger equation says is that the Hamiltonian operator causes the wave function to collapse to a definite point. This should sound familiar. The eigenfunction represents the quantum object as a wave, whereas the eigenvalue represents the quantum object as a particle. And these two characteristics are actually self-dual to one another, as we know from the wave-particle duality formulation of quantum mechanics. So thus the Schrodinger equation and what's called the quantum wave function collapse is another way of looking at wave-particle duality, is that the wave is the Hamiltonian operator, the particle character of the quantum object is the eigenvalue, and these two are actually self-dual to one another. So the wave function is all about how an abstract potential represented by this mathematical space of the wave function collapses into a particle with a definite position. So how does it select out of all of these different possibilities? How does it select one reality? How does it select one attribute to actualize? And in its simplest form, the Schrodinger equation says that an operator collapses into an energy value. So through the collapse of a wave function, an operator becomes a definite value. But let's simplify this to just think about it in terms of a deck of cards. We've thrown a lot of complicated language at you. It's like a card game. The wave function psi is a shuffled deck of cards consisting of 52 eigenvalues corresponding to every possible card and suit combination. So within that space of potential is you have the possibility of drawing an 8 of clubs or a 6 of diamonds. Anything that is possible within the deck is actually represented within that wave function. So the Hamiltonian, who you can think of as the person who is drawing the card, the Hamiltonian operator picks up one of those cards. It selects one card from the deck, one eigenvalue from the eigenfunction. And H hat, the Hamiltonian operator, represents the person who picks the cards. And E, the eigenvalue, is the card he picks. So the eigenfunction is a space of eigenvalues, and it is not all of those are selected. In fact, only one of them is selected. Only one position and momentum of the only one position of the quantum particle is selected out of the infinite space of possibilities, and we can't know for sure where it's going to end up. We can only make predictions based on the mathematics. So the only question remains is, why was one card picked instead of all the other cards that could have? So in other words, why is this eigenvalue different from all other eigenvalues? Why did the quantum operator choose to select this value rather than anything else it could have selected? And this is an excellent question. But basically, the way you have to think about this is a quantum object's wave character represents the abstract space of potential, the deck of cards, prior to the object occupying a definite position and momentum. The particle represents the actualized or collapsed phase of the wave not just an abstract potential for me. It's actually Queen of Hearts. It's actually a card that I have in my hand that I can look at and see its attributes. And it's not going to change when I keep looking at it. But then once I take my eyes, the card gets swiped back, and now there's a new Hamiltonian operator that is applying its energetic distribution to the wave function. So it follows that the notion that quantum objects move is actually, it's just that. It's an assumption. It's a notion in our minds, but isn't backed up by concrete reality. All that we see are stationary attributes. So the position and momentum of a quantum object doesn't change while we're looking at it, and then at a later point, it's at a different position. And so to call that motion in the standard sense is an assumption. Somehow, even if it is motion, it seems to be something that is at least related to our observation of the fact, because it's not moving while we're looking at it, but as soon as we look away, it's like a game of freeze dance, it starts moving again. So what is happening in between these registration events? It follows that according to the most common interpretations of quantum mechanics is that the reason why it only changes when we are looking away is because it actually changes from a particle while we're looking at it to a wave while we're not looking at it. So it follows that in between collapses, quantum objects have only a wave character. And this is, you can look up the double slit experiment. You can look up a couple of these scientific experiments which have shown that light and quantum objects definitely have a wave character, in addition to a particle character. So quantum objects have only a wave character in between these collapsed states when we're looking at them. And then after the collapse, they have only a particle character. We can't see that wave function ever. So the wave function is just interpolated from the facts. We don't actually know that it's there because no one's ever seen a wave function. It's like a mathematical space. It's like saying, has anyone ever seen y equals mx plus b? It's just a possible equation. And so again, but then we know that it's there because there's something that is applying to this quantum object to form a space of potential that then becomes a definite object. So what causes the collapse of the wave function from an abstract space of potential to a definite reality? If you ask any physicist, and I'll wager your money on this, they'll either give you a self-assured answer or shrug and say, I don't know. So either they'll be very confident or they don't know at all. And either way, there's no agreed upon explanation for the wave function collapse. There are a number of explanations that people have proposed, but none of them have been proven yet. So to examine this further, we'll look briefly at the conceptual deficiencies of quantum mechanics before examining in turn the at least 7 different explanations that have been proposed to explain the quantum wave function collapse, including the seemingly wild ideas that we live in a multiverse with an infinite or nearly infinite number of parallel universes running simultaneously to our own, that conscious observers like human actually create reality, that we are actually ascribing properties to the quantum system, and much more. So things are about to get absolutely wild. We're going to go into all of these different possibilities and interpretations of the quantum wave function collapse. And this is the central problem of quantum mechanics: is what is actually causing a wave to turn into a particle. And the Schrodinger equation opens the door to the most exciting developments in modern reality theory, the interpretation of the quantum wave function. Although this might just seem like an odd mathematical construction, it is the gateway to deeper quantum realities and deeper understanding of our own reality. Because ultimately, what we're talking about with every single one of these lectures is our own universe. We're not talking about something out there. We're not talking about some abstract idea. If one of these theories is correct, it describes everything that we've ever seen. So this is not light stuff, but thank you. God bless. Take care.